start today's lecture, not lab. So this topic here in chapter 15 has to do with ice tables. And particularly, we will concern ourselves with ice tables anytime we're talking about a weak acid or a weak base. If you see a weak acid or a weak base, and then we want to calculate the pH. Okay, then we need the ice table. Now, to make our life a little bit easier with the ice table, we can do what's called the low ionization assumption. So we'll do that for your test. We will not, or at least I will not have you do the quadratic. Okay? So we will assume the ionization of weak acid to give you H plus is very small, less than 5%. In calculating the pH. So when it's less than 5%, you can use the low ionization assumption. That is percent ionization. Right. So let's do another problem here. Okay, this one will be calculate the pH of a 0.26 molar methylamine solution. Okay, so methylamine is actually a weak base. Okay, so how do you know it's a weak base, or how do I know it's a weak base? Just because I know amines, and remember functional groups. Okay, functional groups, the alkanes, the alcohols, the esters, way back in chapter 11. Okay, the amines are just another type of functional group. I'm sure if you take organic, Dr. Kim will mention this to you and teach this to you more than I will ever. But this is a weak base. Okay, so the amines. And methylamine is a type of functional group known as an amine, and it's a weak base. Okay, so I'll give you the formula for methylamine. Okay, so I'll give you that. Okay, so I'll give you the formula. And we are asked to find out, let's keep focus on the problem here. The focus on the problem is to calculate the pH, okay? The power of the hydrogen ion concentration. So in order to do that, we need the equation here. It's a weak base. Okay? It's a weak base. So the first thing you need to do is draw or write the equation for this. Right, so the equation for a weak base is anything that gives you OH minus. Weak base gives you OH minus. What will weak acid give you? Okay, H plus, right? Acids will give you H plus, bases will give you OH minus. So this methylamine, as all amines, are a source of OH minus. This is the equation that does that for us. Okay, a base such as methylamine will take a proton from water and give you OH minus. And this is CH3NH3 plus. Okay. All of this is happening in water. All right, so this is a weak base, as all amines are. So really, we're not talking about Ka here. We're talking about Kb. Okay. So I'll give you the Kb. Okay, so the Kb. Why are we saying Kb instead of Ka? Because it's a weak base, and what do weak bases give us? Okay, OH minus. So the Kb, which is given to us, I'll give you that. It's 4.4 times 10 to the minus 4. All right, so back to our problem here. Okay, 0.26 molar. Okay, 0.26 molar. So we have a bottle. Imagine you have a bottle of 0.26 molar of this methylamine. Okay, bottle of this chemical, it's asking you for the pH of this. Okay, so it's 0.26 molar bottle of methylamine. Okay, we'll do our ice table. Okay, water is a liquid, so you don't worry about that. Okay, some of it will go this way. Some of it will go this way and be a source of OH minus. 4.4 times 10 to the minus 4 is this Kb, so predominantly it's here, but some of it will go this way. So this will be that sum that will go to the right or this way is minus x plus x plus x. That is to say, some of this methylamine will perform this reaction. Okay. So at equilibrium, this is 0.26 minus x, this is plus x, and this is plus x. Right, this is the equilibrium concentrations. Okay, so we'll plug it into our equilibrium expression. Okay, so 4.4 times 10 to the minus 4. Okay, OH minus is x. CH3NH3 plus is x, x plus x times x is x squared, plus 0.26 minus x. So here we'll use the low ionization assumption. The low ionization assumption is that we will assume this reaction moving in the forward direction, we'll assume is negligible. Okay, it's negligible. So basically what we're saying is that we will assume x is small. That is the percent or the amount of the reaction going this way to give us OH minus and CH3NH3 plus is significantly small, such that 0.26 minus x is essentially 0.26. Okay, that is to say, that is, assume x is small. Okay, when we assume x is small, then 4.4 times 10 to the minus 4 equals x squared divided by 0.26. This is called the low ionization assumption. Our cutoff is about 5%, if you remember from last Friday's lecture. So 4.4 times 10 to the minus 4 times 0.26. Okay, we'll square root that to give us x. And what is this on our calculator? 4.4 times 10 to the minus 4 times 0.26. Okay, we'll square root that. 0.0107, big M. Okay, don't forget the units. The units are big M, molar, moles over liter. So what does this X represent? Alright, so this X represents this X, which is the concentration of OH minus. So before calculating pH, let's calculate POH. Okay? From calculating the POH, we can get our pH. So pH is minus the log of the OH minus concentration, which is minus the log of 0.0107. Okay, and what is that on our calculator? Minus the log 1.97. This is not our answer. Okay, therefore, what will our pH equal to? Okay, our pH will be 14 minus that, remember? Okay, so what's 14 minus 1.7? 12.03. This is the answer. So the pH is going to be 12.03. Okay. So, is that basic or acidic? Well, methylamine is a weak base, so it's going to be basic. Okay. We predict more OH minus than H plus. Okay. Above 7, then it's basic. All right. So that is how we do this type of problem. Okay.
Why is it minus X?
Because some of it is going to go this way. So you have a bottle. Imagine you have a bottle of 0.26 methylamine, the name of this chemical. It's not just 0.26 methylamine by itself, Asia, because some of that will react with water to give you this and this, some of it. So inside this bottle is not just this, because the solvent will be water, always water, at least 99% of the time. Because the solvent is water, this chemical will react with water to give you this and this. So to what extent it does is based upon the Kb constant, which is a constant. I'll give that to you. So the extent to which this will go this way and react with water to give you OH minus and the CH3NH3 plus is given by minus X plus X plus X. Okay, some of it's going to go this way, not 100%. If it was 100%, it would be a strong base. Okay. If it's 100%, it's a strong base. You just plug it into the pOH equation. Thank you. So yeah, it's a good question, but this is how you want to approach this type of problem. This is how you'll solve this type of problem. So speaking of weak bases, if you look at page 16 of our notes, we see some examples of weak bases, okay? So it's hard to read all of this, that's fine. I'm going to give you the constants. You do not have to memorize any of these constant values for Ka or Kb, but most of these weak bases, okay, again, I know you can't read them. Most of these weak bases, if you look at them, you have their amines. Okay, they're amines, which is a functional group that you'll probably see in organic chemistry if you take it. Okay. Right, so you have your conjugate base, you have your conjugate acid, so on and so forth. All right. By the way, let me go back to this problem here on page 15 for a second. Yeah, so on an exam, if I give you this equation, okay, what would be the acid and what would be its conjugate base? Okay, so which one here is the acid and which one's the base? Okay, this is the base. Okay, what will this be? Okay, what's the conjugate base to this acid, water? Okay, this is the acid. It gives up the H plus, which is what acids do. So what is its conjugate? Is it this or this? OH minus. So these are conjugates of each other. So this takes that proton. It's the base, because bases take protons. What would its conjugate be? CH3NH3 plus. Okay, so this is the conjugate acid. Right? So on an exam, make sure you know the conjugates of each other. These are conjugates. So these two are a couple based upon giving and taking an H plus proton. These two are a couple based upon giving and taking an H plus proton. so here's some relationships. Okay, I think we went over this, but I want you to keep in mind, I know it's fall break, and you may have forgotten this, but a high pKa means it's not a good acid, it's a weak acid. Okay. I'm sorry. See, I told you I'm coming through fall break. A high Ka. Okay, let's say you have $1 million. Are you moving forward? Okay. Yes, you're moving forward. So if you have a high Ka, this means a strong acid. But that means a low pKa. Okay. Okay, so high Ka means low pKa. This both means strong acid. A low pKb, okay, a low pKb means, this also means a strong acid. Okay, and a low pKb, a low Kb, excuse me, corresponds to a high pKb, so this also is a strong acid. Okay, so remember that Ka times Kb is equal to Kw. Okay, so if you have a small Kb, it means you have a large Ka, and we just said a large Ka means a strong acid. So this represents the situation of strong acids. What represents the situation of a weak acid or strong base would be this. Okay, low Ka means a weak acid, a very small number. This is where we use the low ionization assumption. High pKa means a weak acid. Do you remember the formula for power of Ka? pKa is minus the log of Ka. Okay, high Kb means it's a very good base, but if it's a good base, that means it's a weak acid. High Kb means it's a good base, a good source of OH minus, and low pKb also means a weak acid. High Kb means it's a good base. High Ka means it's a good acid. So make sure you get these, clear in your mind. If you're going to rank an acid, okay, if you rank an acid, what would be the strongest acid? Like on the exam, ranking an acid, or maybe on this quiz where you have to rank an acid. Okay, what are you looking for? Okay, you're looking for the highest Ka, right? Mm-hmm. Or the lowest pKa. That would be the strongest acid. What would be the weakest acid? If you were to rank them on your quiz or on your exam, the lowest Ka and the highest pKa. Okay, so the ranking of acids is an important part of your test in this quiz. That's going to, do whenever your test is. So this would be the strong acid. This would be weak. Okay, ranking acids. Which acid is better than the other in terms of strength? All right, can I move on here? Everybody is all right, okay? Yes, okay. All right, let's move on to page 17. Let's do this problem together, and then we'll wrap up this chapter. Right. Which way does the equilibrium shift in the following reaction, right or left? Equilibrium, okay, how do we know this is an equilibrium reaction? We see our arrow, it goes back and forth, all right? But which way does this equilibrium sway? Does it sway more towards the left, the reactants, or does it sway more towards the right, the products? Okay, so let's just give some identities here. CH3COOH is acetic acid. HCOO minus is formate ion. CH3COO minus is the acetate ion, the conjugate. And then HCOOH is something that took that proton. This is called formic acid. All right, so the pKa of acetic acid is 4.76. The pKa of formic acid is 3.75. So which one is stronger, acetic acid or formic acid? Which is stronger? Acetic acid is stronger. Remember the trend? Okay, the lower the pKa, the higher the Ka, which means stronger acid. So that's the trend. By the way, let's calculate the Ka, okay, so that you get practice for the test. What is the Ka for acetic acid? Okay, we know the pKa, what's the Ka? Okay. So it's going to be 10 to the power of minus 4.76. Okay, and what is that on our calculator? Anti-log minus 4.76. (1.74 times 10 to the minus 5). Okay, so that's the Ka of acetic acid, which corresponds to a pKa of 4.76. Let's do the Ka of formic acid. Okay, anti-log to the minus 3.75. Okay, so what's the anti-log of that? Okay, minus 3.75. 1.78 times 10 to the minus 4. So which would be the stronger acid now? Something that goes 1.74 times 10 to the minus 5 this way, or something that goes 1.78 times 10 to the minus 4 in the forward direction? Okay, which is larger? Okay, this is larger by 10. Okay, 10 times larger. So that implies which is the stronger acid, formic acid or acetic acid? Formic acid. Yes, Leslie? It's formic acid. Okay, so if this is the stronger acid, which way will the reaction shift? Okay, so this is a better acid, so this is better at giving away protons, right? It's a better acid. It's better at giving away protons. So since it's better at giving away its proton, the reaction is going to favor this way, the left-hand side. Formic acid is just a better acid. Okay, it's better at its job of being an acid 10 times. So this is 10 times larger than that. So formic acid is a better acid. And then acetic acid. And since it's a better acid than acetic acid, it's going to give off its proton better. Okay, which means you'll have more of the reaction going towards the left, more of the reaction giving you the conjugate, which in this case is formate. Okay, and it's a better acid, so it's going to do a better job of protonating this acetate to acetic acid. All right, let's do a ice table problem, this time with a weak acid. All right, what is the pH of 0.6 molar formic acid solution? The Ka of formic acid is 1.8 times 10 to the minus 4. So formic acid has this formula. Okay, remember functional groups? There's a functional group called carboxylic acids, which you'll probably learn about if you take higher level chemistry classes. So this proton is ionizable. And it has a Ka of 1.8 times 10 to the minus 4. So again, just like our last example with the weak base, I have 0.60 molar formic acid. Okay, some of it will react with the water. Okay, so this is the equation for that. Okay, I'll give you the formula, but you need to write this equation. That's your responsibility, because I want you to know, how this contributes to pH. It does so through this equation. Okay, formic acid, the acid gives away the proton. And then you have H3O plus. Okay, plus the conjugate, which is formate. So some of this will react with the water in the bottle. This is not just by itself in the bottle, by itself, all alone. Because the solvent is water, we'll have this reaction. And some of it will go this way. Some of it will react with the water. How much? Okay, we'll do our ice table. Okay, so initially we're at 0.60. Water is a liquid. Okay, this is 0 initially and 0. Some of it will go this way. So minus x plus x plus x. So 0.60 minus x plus x plus x. Just like we did with the weak base, we'll plug it into our equilibrium expression. Ka is H plus times HCOO minus divided by HCOOH. All right, the Ka for this problem is 1.8 times 10 to the minus 4. Okay, at equilibrium, this is x, and then HCOO minus is x. X times x is x squared divided by 0.60 minus x. Okay, we will assume x is small. And when we assume x is small, 0.60 minus x is about 0.60. 0.60 minus x is about equal to 0.60. So this makes our math a little bit easier. Okay, this is called the low ionization assumption. Okay, we will assume it ionizes less than 5%. Low ionization assumption. Okay, so 1.8 times 10 to the minus 4 times 0.60. Okay, we'll square root that. This equals to x. So 1.8 times 10 to the minus 4 times 0.60. Okay, 1.08. Okay, square root that. Put this again here. And we square root this to get x, and we're getting 0.0104 big M. Okay, 0.0 equals x. Okay, so don't forget to square root it. Okay, we need to solve for x here. Okay, so what does this x symbolize? Okay, this x symbolizes this x, which symbolizes the concentration of H3O plus. So now we can figure out the pH, and the pH is minus the log of the hydrogen ion concentration. Point 0.0104. And what's minus the log of 0.0104? Minus the log of this answer. 1.98. So I'm getting a pH of 1.98. So we did two ice table problems where we did the low ionization assumption. One of it was for the weak base, and the other one was for the weak acid. So let me just tell you about this assumption here, low ionization assumption. Okay, the threshold is 5%. Okay. So let's see how much this gets ionized by. So we'll take our x, which is 0.104, divided by the concentration in the bottle. So what is the concentration in the bottle? Okay, 0.60. Okay, we'll times it by 100, and that's our percent ionization. .0104 divided by 0.60. Times 100, 1.7%. Okay, what is the threshold? Okay, 5%. So this is 1.7% ionized. It's well below 5%, so this low ionization assumption is valid. Assuming x is small is valid, we don't need to use the quadratic. We can just go ahead and assume 0.60 minus x will essentially is 0.60. All right, 1.7% is less than 5%. All right, any questions on this? So get comfortable doing this. We'll do a lot of these in this chapter as well as in the next chapter. Okay, and you can use the low ionization assumption to get your pH and pOH. The first example we did was with methylamine, which is a weak base. We got Kb. And then this example we did it with a weak acid. This was called formic acid. All right, so are you guys comfortable doing this ice table? Okay, and this low ionization assumption. All right, let's wrap up this chapter here. All right, so this is basically telling you this equation, Kw is Ka times Kb. So not much there for me to tell you guys. Kw, if you're interested in pursuing this class, higher level classes or more chemistry in your life, then you might as well memorize this number for Kw, which is 1.00 times 10 to the minus 14. And obviously all our Ks are quoted at a specific temperature. This Kw of 1.00 times 10 to the minus 14 is at 25 degrees, which is what you get from your textbook. All right, so the next topic here is polyprotic acids. This basically means some acids can give off more than one proton. Okay, can give off more than one proton. example here is phosphoric acid. Okay, how many protons do you think phosphoric acid could potentially give off? How many? Okay, it can give off 3 H pluses. All right, the first one, okay, you can follow along with me. The first one gives you H3O plus, and then the conjugate. Okay, that one has a Ka of 7.5 times 10 to the minus 3, pKa of 2.12. Okay, that's good. But look, what do you notice about this H2PO4 minus? Okay, that H2PO4 minus can give off another proton and give you HPO4 minus 2. Okay, what's the Ka for that proton? 6.2 times 10 to the minus 4. pKa is 3.21, so this second proton is a little weak. Okay, this first proton goes off at 10 to the minus 3. This proton goes off 10 times lower, 10 to the minus 4. So the second proton is pretty weak. Okay, what about the third proton? Do you guys see this HPO4 minus 2? Okay, what can that do? Okay, it can give off its final proton right here. And when it does that, it gives you inorganic phosphate, PO4 minus 3. Okay, inorganic phosphate, what we have in our cells. Okay. What about that third proton? 10 to the minus 13. Wow. Okay, is that acidic? That's very, very small. Okay, this does not happen. If it does, it's very, very small. Okay, so the third proton, it's just poorly comes off. The second proton at 6.2 times 10 to the minus 4 comes off, but it's not that great. And then the first proton that comes off at 7.5 times to 10 to the minus 3 is also not good, but better than the other two. Okay, just check out the values of these. Check out the values. So you notice that this is becoming less and less acidic. Okay? And this is the trend. Okay, this is the theme. The first proton comes off easy. The second proton comes off not so easy. And the third proton doesn't come off at all. Okay, so subsequent protons are less and less acidic. Okay, so each successive proton removal becomes harder. Okay, for polyprotic acids. Okay, you see that here, 7.5 times 10 to the minus 3 for the first acid. Okay, to give you H2PO4 minus, dihydrogen phosphate. But look at that, the second one comes off at 6.2 times 10 to the minus 4, pKa 3.21. All right, and then the third and final proton comes off at 4.8 times 10 to the minus 13. Okay, that's super, super, super small. Okay, so the first proton is acidic, the second proton is not so acidic, the third proton is not acidic at all. So that's the trend for polyprotic acids. First proton is acidic, subsequent protons less and less acidic. Okay. Okay, so polyprotic, more than one proton that can be given off. First proton comes off. The first proton comes off acidic, second, third protons not so acidic. And what I want to instill in your guys for teaching purposes is that the first proton has a high Ka, low pKa. The second proton has a low Ka, pretty high pKa. And the third proton, which is so ridiculously small, has such a small Ka, but a very, very high pKa. This is the trend for something that's becoming less and less and less acidic. Okay, lower Kas, higher pKas. Okay. All right, so that's the trend we see for polyprotic acids. We also see that for another diprotic acid, H2SO4. And there's another one called oxalic acid, H2C2O4. Okay, this can give off 2 protons. This can give off 2 protons. The first proton is acidic. The second proton not so acidic. Okay, these two are what are called diprotic acids. Okay, giving off 2 protons. This can give off 3 protons. This is called phosphoric acid. So I will not ask you this on the exam. So and we don't have Blackboard. We switched a couple of years ago to Canvas. So, anyways, Blackboard, Canvas. What's the big deal? You can check this out, but I will not ask you this on the exam. It's basically doing an ice table, but you're doing an ice table on a polyprotic acid. In this case, the diprotic oxalic acid. Okay. So you'll need 2 ice tables. Okay, so you can check out that if you have some time, and if not, that's okay. I will not ask you this, but this is kind of advanced. If you know how to do this, or at least understand it, then anything on the exam should be very, very easy. And you're going to need 2 ice tables if you do plan on doing this problem. You're going to need an ice table for this. It gives off its 1 proton, and then you'll need an ice table for that, the second one. Okay. So for this proton, so 2 ice tables. All right, and let's conclude the last 5 or so minutes of this chapter with some strength of acids. These are acids that have a halogen in them. Okay, halogenated acids. Halogens are in group 7 of the periodic table. Those are the halogens. So we're talking about HF, HCl, HBr, HI. Okay. So the acidity increases, but also the radius, the atomic radius increases as well. So the size increases. So with that size increase, the atomic size increases, comes increased acidity. Imagine if I'm a big guy and you're so small. Okay, it's easy for me to grab you and just hug you. Okay, grab, because iodine, bromine, chlorine are just big molecules that will take the really, really small proton. Okay, and then these are all electronegative also as well. Okay, these are very polar molecules. Okay, fluorine is small, so fluorine, it being small, tends to be considered kind of a weak acid. Okay, weak acid because of its small size. And you can see here, to break that bond is a lot of energy. To break the HF bond is 568.2 kilojoules per mole. So that's makes HF a weak acid. So the bond is strong. They're 2 small atoms coming together. They have a good interaction. So HF is kind of a weak source for protons. Okay, the other ones have less energy. Okay, more has to do with their size. Okay. And the final thing I want to tell you guys is that electronegativity, okay? Okay, will make a substance more acidic. Okay, fluorine is electronegative. Chlorine is electronegative. Bromine, iodine are electronegative, so they pull. They pull. Okay, remember the very first week of class I talked a lot about water? Okay, water can be a source of an acid. Okay, we see this, a Brunstad acid. This hydrogen-oxygen bond is not a 50-50 bond. Okay, it pulls, it tugs on this, and then you have a partial negative on the oxygen end. It also pulls and pulls on this bond here, so you have a partial positive on the other end. That oxygen is partial negative. So this is the reason why water can be a weak acid, because it can pull, and given the right environment, or given other molecules, this proton can come off. Okay, so the pulling power can make the proton go away. Okay, because it pulls, essentially pulls all of its electrons, and then the H plus comes, and then the H comes off as H plus. Okay, so electronegativity is very important in determining whether something is a good source, where it pulls so much that that hydrogen leaves off as an H plus. So we see that here in our last page of our notes. Okay, which do you think would be acids would be more weaker, HClO2 or HClO3? So which has more oxygens? Okay, so which has more pulling power? Okay, so the one that has 3 oxygens will pull. So if it pulls, this has a tendency to come off as H plus, just because it's like a tug of war. 3 oxygens will tug on that one hydrogen and make it go away as H plus. Whereas this owns 2 oxygens, less electronegativity, less polarizability. So this would be a weaker acid, just because you have less electronegative oxygen atoms. Okay. Okay, so less pulling power because of 2 oxygens versus 3 oxygens. All right. And then a couple of more things here really quickly. Give me one more minute. I'm almost done. So just wrap up points here. Okay, wrapping up points. Acids and bases. Look what can give you a base. Okay, sodium oxide with water can give you a base. CO2 gas with water gives you an acid. Okay, this is important in the blood. I don't know if you plan to take biochemistry or, other those types of courses. This one, it happens in the blood. It also happens in the lung. So CO2 that we exhale or take in reacts with water to give you an acid. Actually, this acid gives you bicarbonate in our bodies. This gas gives you nitric acid, which is one of our strong acids. So very, very different sources of acids and bases. Okay, some solids can give you acids and bases. Some gases can give you acids and bases. All right, and finally, we were talking about Brunstad acids and Brunstad bases. Lewis bases and Lewis acids have to do with electrons. Okay, so a Brunstad involves give or take an H plus. A Lewis base has to do with giving or taking of an electron pair. Okay, so this gives electron pairs. Okay, and this takes electrons. Okay. In this chapter, we were focusing on Brunstad. Okay, Brunstad acids give H plus. Brunstad bases take H plus. So here are all our studies, and all our problems were on Brunstad acids and bases. You'll see Lewis acids and bases when we talk about things in terms of electron pairs, giving or taking electron pairs. You'll see that in organic chemistry, definitely. Okay.